Hello, this video is about the boundary of a surface, and the boundary of a surface is needed to state the theorem, well, Stokes' theorem, and in Stokes' theorem we need to have a precise notion of the boundary. So what is the boundary of a surface? Well, first of all, let's clarify what a surface even is. So the idea of a surface is that it's some object. So for instance, you could have a sphere. This is a surface. And what makes it a surface is that at each point on the surface, let's call this point P, there's a neighborhood around that point that's mapped onto it by an open set in R2. So basically what that means is that if you look at the points near P that are on the surface, then there is a way to take an open set in R2, say the origin here, and there's some neighborhood, some open set around the origin, such that when you take this open set, you can map it directly onto this open set centered at P here. So something like that is called a coordinate patch. And basically what a surface is it's something that's covered by coordinate patches. So if you have a point, any point on the sphere, there's some way to take an open set, let's say the origin, an open set containing the origin, that will map onto a patch of the sphere. And you can cover the whole sphere by these patches. And that's basically what a surface is defined to be. So the idea, intuitively, a surface is something, it's a set that can be covered by coordinate patches in R2. And the coordinate patch, well, I'm being a bit loose here, but it consists of an open set in R2 and an open set in this set S. So in this case, your sphere would be S, such that there's a way to map in a one-to-one and onto fashion an open set in R2 to an open set in S, and that will cover all of S. Okay, that's the idea of what a surface is. So for instance, you can have say, like a cone. You can have this cone. Technically, we should exclude the origin. But if you have this cone, then you can take, again, patches that will cover the cone. So, for instance, if you have a point on the cone, you can take some piece like this, and then there's going to be some open set at the origin that will map in a one-to-one and onto fashion onto this patch, onto this blue set, and then you can imagine covering for each point. So you can cover up the cone with all these patches. With open sets in R2. So like you could have an open set in R2 that goes to this patch, and then there's another open set in R2 that goes to that patch, and then there's another open set in R2 that goes to that patch, and you can cover up the surface with patches. So you can basically take these open sets in R2 and then map them, so you can take like all of these, right? All of these, and then kind of patch them together to produce this cone. And that's what makes the cone a surface. Okay, so I don't want to get too detailed about this, but this is the intuitive idea about what a surface is. It's something that when you take a point and zoom in, and you look at the points, if you take a point on the cone, and then zoom in, and you look at the points in the immediate vicinity of that point that are on the cone, it looks like R2. Right? It looks like an open set. Right? It's sort of like on the Earth. If you have a point on the Earth, if you look at the immediate vicinity, it looks like a plane. Right? It looks like R2. I mean, if you look at the ground, it looks like a flat plane. And it's the same with this cone. Okay. Technically, there's an issue with this point here, which makes it a problem because it's a sharp corner, and so technically, to be a surface, you have to look at the cone except exclude the origin, or exclude this vertex. But anyway, that's the idea of a surface. But you can also have. So those are examples. Where you're covering things with open sets in R2, but let's look at this cone, and let's look at this piece here in purple. Okay. Let's say you have a point here. You look at a point here. Now this point does have a neighborhood. Let's say you look at the points close to this point P, but you look at the points that are on the cone that are near it. Well, if you look at how to map that by R2, that's not going to be an open set in R2. Okay, that's going to be something that looks like this. It's a solid region. Well, it's not there's a solid line here that will go to this edge, and then the interior points here will go to the interior points here. Okay, so this is not an open set in R2, right? That's not an open set in R2. Technically, when I'm looking at these patches, since I'm looking at open sets, I really should have made these dotted, because I'm not including the boundary. So open sets. Okay. This one's an open set in R2. But when you look at this point here, okay, when you look at the immediate points near it that are on the cone, and look at how it can be covered by a patch, the patch is not going to be an open set in R2. And when you have something like that, the point is called a boundary point. So this point P is a boundary point. It's a boundary point. So a boundary point on a surface is a point that is not covered by an open set in R2. Okay? So what would be the boundary points of this cone? Well, if you think about it, it would be all these points, and this, technically we should be talking about the cone excluding the origin. Okay? When we're talking about the cone excluding the origin, the boundary points are the points on this circle. And the collection of boundary points is naturally called the boundary. So the boundary points of a surface is called the boundary of the surface. And sometimes the notation is if you have a surface S, so S is, in this case, is your cone, excluding the vertex, then the surface, if the surface is called S, then the boundary is often written as this partial symbol S. Okay. So let's look at an example. Let's look back at the example of the sphere. Okay. Does this sphere have a boundary? Well, remember, when we're talking about a sphere, we're talking about the set of points that are a fixed distance from a certain point. So we're not including the sort of inside of the sphere, right? We're not looking at, so for instance, if you're talking about the unit sphere, it's the set of points that's exactly 1 unit away from the origin, not less than or equal to 1 unit away. That's called the ball, a solid ball. But we're talking about a sphere, and the sphere can be patched together by open sets in R2. Whenever you take a point on the sphere, okay, when you look at the points in the immediate vicinity, it can be covered by an open set in R2, like that. So what that means is that the sphere does not have a boundary, because every point can be covered by a patch that is actually an open set in R2. Or more specifically, we should say that the sphere, the boundary of the sphere, of this sphere, the boundary of the sphere is the empty set. So this is an example of a surface without a boundary. And that's in contrast to this cone. And let's take a look at another example. So suppose that you had something like this. So this is a surface in R3. Okay. What's the boundary of this surface S? Well, it's going to consist of all the points here. Because any other point is going to have some open neighborhood that can be covered by an open set in R2. Even the ones at the sort of the top of the surface, right? When you look at the top of the surface, okay, it's going to have a neighborhood which is kind of like wobbly, but it will still be covered by an open set in R2. Okay, but this point will not be, it's not visible in the picture, but you'll be able to map it in the one-to-one onto fashion from an open set in R2. However, if you look at the points here, okay, and you look at the points close to it, any patch is going to look like this, which is not an open set in R2. It's what you get when you take an open set in R2 and then intersect it with the upper half plane. So if you look at, I don't want to get too carried away by this, but the point is that if you look at R2, but then you only look at the points where the y coordinate is greater than or equal to 0, and then you take an open set in R2 and then look at the intersection with that upper half plane, then you get something like this. So this is considered an open set in the upper half plane, but it's not an open set in R2. So that's why this point is a boundary point. And when you look at all the boundary points, you're going to get this part. So that's the boundary of S. And it's a theorem that, and I'm stating it loosely, but when you have a surface, the boundary of a surface is a curve. That's a theorem. It's in some sense like one-dimensional. Okay? And maybe we'll do one more example. So suppose that you had something like the set of x, y, z such that x plus y plus z is equal to 1, and x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0. So what that would look like is, so here's the x-axis, positive x direction, positive y direction, positive z direction, and then you have this plane that goes through 0, 0, 1. This point would be 1, 0, 0, this point would be 0, 1, 0, and then this point would be 0, 0, 1. All those points lie on the plane, and so the plane is just the plane that contains those 3 points. And so you're going to get something like this, but then you're only looking at the parts where you have this plane, but then you're only looking at the parts where x and y and z are all non-negative, and so you really just get this piece. It's like a triangle. It is a triangle. Right? And again, there's some ambiguity here because from the strictly mathematical point of view, there's an issue with these vertices because the vertex, it's like a sharp corner, and that's excluded. There shouldn't be a sharp corner in the definition of a surface. But anyway, if you just kind of exclude those vertices, these 3 vertices, you do get a surface S. Oops. Okay. I don't know how to prevent that from happening. Oh, I think I have to do undo or something. Well, anyway, you get the surface S. Okay. Now what's the boundary of this surface S? It's going to be the points along this triangle. Oh, can I make it a different color just to... It's the points along this triangle. Because when you take a point on this triangle, let's call it P, and then look at the points near P, so you just take like a small sort of radius centered at P, and then look at the points that are in S. Okay, that set is going to be covered not by an open set in R2, but it's going to be covered by one of these kind of sets, which is the intersection. So this is supposed to be dotted, but you have this set that's not an open set in R2, but it is an open set in the upper half plane that will map in the one-to-one onto fashion to this set centered at this set that contains P. So the points on the triangle, that's the boundary. So this triangle is the boundary of S in this case. Okay. Well, I hope that clarifies, that gives you an idea intuitively of what the boundary of a surface is. Again, this is a largely intuitive discussion because I never gave a precise definition of a surface, and without a precise definition of a surface, it's hard to give a precise definition of the boundary. But if you understand the precise definition of the surface and the boundary, it's pretty much what I told you. And a reference, if you want a more advanced book, it's analysis. One reference is Analysis on Manifolds by Munkres. He's famous for a topology textbook, but he also wrote some other books too. And one is this Analysis on Manifolds book. And for the context of a surface, he talks about a general concept called a K-manifold. And when K is 2, you get a surface. So a surface is a 2-manifold. Okay. Maybe I should also add that there's also such a thing as the boundary of a curve. So, if you can have the boundary of a curve. And what's the boundary of a curve? Well, so a curve is something like this, right? But suppose that you have these endpoints. Well, when you look at an endpoint, let's call this endpoint P, and then look at the points near it, right? So you look at the points, you look at, say, let's say this curve is in R3. Okay, so this is a curve in R3. And you look at a ball of radius, some small radius centered at P, and then you look at the points that are on this ball, right? So you have this ball, you look at the points that are maybe a distance less than 1 away from P, that are on this curve. Let's call this curve C. Well, that's going to be this piece here. And then what that piece looks like is it looks like, so here's R1, R1, and it looks like, so this is the point that goes to P, and then it's going to be an open interval here, but then there's a closed point here. So it's not an open interval, it's like a half open interval, right? This half open interval will go to this part. And that's what makes this point P a boundary point. So the endpoints are boundary points. This is also, this point, this other endpoint Q is also a boundary point. So the boundary point of, the boundary of C consists of the two endpoints. If you take a point here, it's not a boundary point because when you look at a small sphere centered at this point, say you look at the points that are like 0.00001 away or less from that point, that are on the curve, you get something which is like this, and then this part is covered by a subset of R1, which is an open interval, right? An open interval will map in a one-to-one onto way to that piece of the curve. This is covered by an open interval. So this point is not a boundary point. Of the curve. But notice that this, right, this is not an open interval. So that's the difference between P and Q and then the other points on the curve. Okay, I hope this helps you understand what is meant by the boundary of a surface or the boundary of a curve. Again, not all surfaces have a boundary. Like this sphere does not have a boundary, but things like this cone have a boundary, and things like whatever the surfaces have a boundary, and what makes something a boundary point is that when you look at the points in the immediate vicinity, basically it does not look like an open set in R2. For the other points are called interior points. So maybe I should just, maybe include it somewhere here, that if you look at S but then exclude the boundary points, that's called the set of interior points of the surface. So every point on the surface is either a boundary point or an interior point. Also, one thing I want to add is that in topology, there's this notion of the boundary of a set. So for instance, you could have R3 and then a set in R3, that's going to have a boundary, but that's a slightly different concept than the boundary of a surface, which is the topic of this video. So if you take a topology course and you learn about the boundary of a set, that's different than what we're talking about when we're talking about the boundary of a surface. Okay, thanks for watching.